Welcome to the cluster architecture section. Now, as a reminder, if you have any questions throughout today's event, please feel free to enter them in the text box below the video. We have Google experts on standby to answer your questions live. Now, throughout today's event, you'll also see quiz questions popping up on the right-hand side of the screen. So please participate to share your knowledge of what you've learned so far. So let's start by looking at cluster architecture. Now, in this section, you'll learn about the construct of a GKE cluster and its various components such as master and worker nodes. Taking a look at a GKE cluster, we see that a data cluster consists of at least one cluster master and multiple worker machines called nodes, as we mentioned previously. These master and node machines run the Kubernetes cluster orchestration system. Now, a cluster is the foundation of a GKE system, Kubernetes system. And the Kubernetes objects that represent your containerized applications all run on top of a cluster. So notice that there are some elements that GKE provisions, maintains, and operates, and there are other elements in your container cluster that GKE does provision, but the user can choose to maintain and operate themselves. Now, the cluster master runs the Kubernetes control plane process. The master's lifecycle is managed by GKE when you create or delete the cluster. The cluster master is responsible for deciding what runs on all the cluster nodes, and this can include scheduling workloads like containerized applications, as well as managing the workload's lifecycle. In addition, it can do scaling and upgrades. And the master also manages network and storage resources for the workloads. The master node is involved with scheduling and managing the workloads along with their allocated resources up to a maximum for the node pool. Now remember, the GKE cluster autoscaler works on a per node basis, and when you configure a node with cluster autoscaler, you specify the minimum and maximum size for the node pool itself. Now remember, the master and the nodes communicate using the Kubernetes APIs. The master is the unified endpoint for your cluster. And you can make Kubernetes API calls directly via HTTP, gRCP, or indirectly by running commands from the Kubernetes command line client, kubectl. You can also interact with the user interface in Cloud Console. All interactions within the cluster are done via the Kubernetes API calls. And the master runs the Kubernetes API server to process and handle those requests. The cluster's master API server process is the hub for all the communications for the cluster. All internal cluster processes, such as cluster nodes, system components, application controllers, etc., act as clients of the API server. The API server is the single source of truth, if you will, for the entire cluster. Kubernetes API endpoints is, per se, a distributed API management system comprising services, runtimes, tools, etc. API endpoints provide management, monitoring, and authentication services. And in GKE, there are also a number of special containers that run as per node agents to provide functionality such as, log collections and intra-clustered network connectivity. The container registry is another item we need to talk about. It's a private container image. It is a single place for you and your team to manage Docker images, perform vulnerability analysis, decide who can access what with very fine-grained access control. And many people use Docker Hub as a container registry for storing public Docker images. But to control access to your images, you really need to use a private registry, such as Container Registry. You can access Container Registry through secure HTTP endpoints, which allows you to push, pull, and manage images from any system, any VM instance, or your own hardware. And in addition, you can use the Docker Credential Helper command to configure Docker to authenticate directly with Container Registry, which makes it easy. An outage affecting the registry, be aware. may cause a failure to do things like create new clusters or upgrade clusters, depending on the specific nature and duration of the outage. And as previously mentioned, a cluster typically has one or more nodes, which are the worker machines that run your containerized applications and other workloads. The individual machines are compute engine VM instances that GKE creates on your behalf when you create a cluster. So each node is managed from the master, which receives updates from each node about its own status. You can exercise some manual control over the node lifecycle, or you can have GKE perform automatic repairs and upgrades on your cluster nodes, as we mentioned earlier. It's up to you. A node runs the services necessary to support the Docker containers that make up your cluster workloads, which would include the Docker runtime and the Kubernetes node agent called Kubernetes. So let's take a brief comparative look at what is virtualization versus what is shared hosts. Now, with shared machines, really, there's no isolation of the system. The system utilizes common libraries. You have applications that are coupled with the operating system itself. If you implement virtualized machines on bare metal, that means that you do have isolation and your system doesn't use common libraries between the virtual machines. But this is kind of expensive to implement and really inefficient. It also tends to be hard to manage. In a container-based system, you have isolation between your applications themselves. They don't implement common libraries, and there's far less overhead and much less dependence on the host operating system itself. So you have true isolation. Now, when implementing container clusters, you specify a node machine type and operating system image. A machine type is a set of virtualized hardware resources available to your virtual machine instance, including, of course, system memory size, virtual CPU, and things like persistent disk limits. You need to choose a machine type when you create an instance. Each node is of a standard compute engine machine type, which you can choose from general purpose, memory optimized, compute optimized machine families. You can select from a number of predefined machine types in each machine type family. Now, the default type is an N1 standard -1 with one virtual CPU and 3.75 gigabytes of memory. But you can, of course, define your own. You can select a different machine type when you create a cluster if the predefined machine type doesn't meet your own needs. And you can create your own custom machine types if you want. Each node runs a specialized operating system image for running your containers, and you can specify which OS image your clusters and node pools will use. You can configure VM instances or an instance template to deploy and launch a Docker container, and a compute engine supplies optimized operating system images with Docker installed. And then it launches your container when your virtual machine starts up. With GKE, you can create a cluster tailored to the available requirements of your workload in your budget. As a rule, when selected, cluster types can't be changed. You do have a choice of creating single zone, multi-zone, or regional clusters. Now remember, a single zone cluster has a single control plane master running in one zone. This control plane manages the workloads on nodes running in that same zone. A multi-zonal cluster has a single replica of the control plane running in a single zone and has nodes running in multiple zones. Now, during an upgrade of the cluster or an outage of the zone where the control plane runs, workloads can still run, but they can't be configured until the control plane's available again. Now, multi-zonal clusters balance availability and cost for consistent workloads. If you want to maintain availability, and the number of your nodes and node pools is going to change frequently, you might want to consider using a regional cluster instead. Now, a regional cluster has multiple replicas of the control plane running in multiple zones within a given region. Now, that's great for high availability. Zones also run in each, nodes, I should say, also run in each zone where a replica of the control plane runs. Now, because a regional cluster replicates the control plane and the nodes, it is going to consume more compute engine resources than a similar single zone or multi-zone cluster. So yes, it will cost more, but it does give you high availability and redundancy. Now here we see an example of a multi-zone cluster. As mentioned previously, a multi-zone cluster has a single replica of the control plane running in a single zone and has nodes running in multiple zones. Cluster type selection is going to impact the cluster's availability, version stability, and whether the cluster is VPC native or route-based, as well as other elements such as, well, network isolation. With Google Cloud Build Service, you can build container images in the cloud. And these images can be imported from GCS, CSR, GitHub, or Bitbucket. Google Cloud Build executes a series of build steps and triggers, and this is done by default by or possibly by user-defined actions. Cloud Build allows you to build your containers in the cloud in a serverless manner, which means you don't need to manage entire fleets of virtual machines for your clusters. So this concludes the cluster architecture section. And in this section, we learned about the construct of a GKE cluster, its various components such as the master and worker nodes, and their relationships to each other. We also talked about the kube control command and how to use it in Google Kubernetes engine clusters to create, inspect, and interact, as well as delete pods and objects. Welcome to the workloads on GKE section of our course. Now this section, our purpose is to dig deeper into containers and how Kubernetes deploys them as compute nodes through the concept of course, pods. Pods allows containers to be managed on a massive scale, and they make Kubernetes orchestration possible. So, at the highest level, Kubernetes is a set of APIs that you can use to deploy containers on a set of nodes. On the left, you have the user. In the middle, you have the master components of Kubernetes. And on the right, you have the Kubernetes worker nodes. The master controls all the jobs that run on the nodes. Now, to be clear, Kubernetes is an open source orchestrator for running a container environment. It can run on a lot of different platforms, from laptops to high availability multi-node clusters, from public clouds to on-premise deployments, and of course from virtual machines to bare metal. Users access the API via command line interface, HTTP, or a user interface. And a cluster, as we've already defined, is a set of computers managed by Kubernetes. It's working as an instance, and everything managed by Kubernetes, of course, is going to be orchestrated by Kubernetes. So the API server is the main interface to all the other components, and it runs on the master node. No direct access to the underlying components is allowed. etcd is a distributed reliable key value store, and it uses a consensus algorithm to make sure that once a key value is written, then all the clients will read the same value for that key. We also have some other components listed here that we'll discuss in turn, such as our scheduler and various other controllers, as well as add-on components that you see. But let's talk about a pod. In Kubernetes, a job is called a pod. It is similar to a VM, and it's the basic unit of deployment for containers. So it can run one or more containers, sharing networking and storage, that are separated from the underlying node itself. Pods, as we mentioned before, are the smallest, most basic deployable objects in Kubernetes. And a pod represents a single instance of a running process in your cluster. Now remember, as we said before, pods can contain one or more containers, such as Docker containers. The containers are managed as a single entity and shared the pod resources, like networking and storage. You can consider a pod to be a self-contained, isolated, logical host containing the system requirements that the application needs for the application it serves. Kubernetes volumes are a way for containers within the pod to share data, and they allow for pods to be stateful. There are a lot of different kinds of volumes in Kubernetes, and some of the volume types include long-lived persistent volumes, temporary, short-lived empty dir volumes, and networked NFS volumes. Kubernetes volumes allow the containers and pods to share data and be stateful, as we mentioned. So remember, you have a pod. Inside the pod, you have the containers and the network interfaces for the containers. And underneath, you have the hardware, operating system, NIC, and all that, as well as a node IP outside address. Data is stored in volumes that reside in memory or persistent disks. So this is analogous to a VM. It's highly portable because you can move pods to other nodes without reconfiguring or having to rebuild anything. And networking between the nodes can be handled by central routing in the master or by other means. GKE uses IP tables and port forwarding in nodes so that nodes can communicate with each other directly, and with load balancers, and so that load balancers don't introduce a single point of failure. So how do you define a pod? Well, remember, most things in Kubernetes are defined via the API. And when you define a YAML document like this one, you upload that to the API server where it runs your containers. Now, after you create the pod YAML file, you upload it to the master. And then etcd on the master creates a pod on your set of nodes. So going back to the definition that we had before, remember a pod file is composed of several different parts. We have things like the API version, as we mentioned, the resource kind, in this case it's a pod, some metadata including pod name, as well as things like a list of containers. So in our case here, we have two containers listed, My App and Nginx. Nginx serves as the app front end on two ports, port 80 and port 443. The containers can talk to each other using the pod's local host network, and My App is the back end that doesn't need to be exposed on the network. So remember, you upload the file to the master, and the master decides which node to run it on. So one of the powerful concepts in Kubernetes is deployment. And this is how you ensure that a certain number of pods are running at a given time. If you upload the pod file as shown in the previous example, you will have one pod running in the cluster, which is fine. But if the pod or the node that the pod is running on stops or restarts, then the pod will not be restored in the cluster. So in order to restore it, you have to define and run a deployment with a replica set that defines how many pods you want running. Now, per our previous example, that would be one. So here's a deployment YAML file, which is very similar, as you might note, to a pod file. And in it, you have things like, well, the resource kind. In this particular case, it's not a pod, it's a deployment. And again, we have metadata with the deployment name and a replica set with the number of pods to run. We also have a selector label for choosing which pods to include in the deployment, and of course, pods with their labels and containers in a template. You identify the group pods with labels and select them in the deployment with a selector. So now in this example, it looks like you're going to run 4 pod replicas with a role set to web, and of course, containers defined for the pod. So then you upload the file, I should say, to the master node. Now, when you do this, the master scheduler is going to decide where to run the pods. So in this case, you want 4 replicas, but notice you only have 3 nodes. So what does the scheduler do? Well, it may double up on pods on one of the nodes. Maybe, or hopefully, the node with the least CPU utilization would be a good option. So now we've talked about labeling. Let's talk about monitoring and health checks, so the nodes know that they're running healthy pods. Each pod that you run can be monitored with a health check, and the health check is run by the node and checks whether the pod is alive and healthy or not. After you define a health check, Kubernetes components on the node, called kubelet, remember that one, issues a health check to the pod that says, hey, are you alive and healthy? Well, if not, Then Kubelet restarts the pod on the same node. And of course, the process continues until Kubelet gets a healthy reply. Now, to define the health check, you specify an API request, an HTTP request, or a TCP port to check on the pod running on the node. And the kubelet continuously checks that particular request or port to make sure that it's successful. So you can get some resiliency out of your app by adding health checks to ensure your application is healthy and, of course, ready to receive traffic. So let's review. Here's a complete overview of a cluster with its key components. You have master servers as a set and worker nodes. The masters provide the control plane for the cluster. The worker nodes run pods with containers in them. Cluster administrators configure the cluster by sending requests to API servers on the masters using a command line tool, remember that one, called kubectl. Kubectl can be installed and run literally anywhere. Now from there, the API server communicates with the cluster itself in two different ways. To the kubelet process that runs on each node, or to any node pod or service through the API server proxy. Now we don't show that proxy function here. Then pods are started on various nodes. Now in this example, remember there are two types of pods running. Some of them are shown in yellow, some of them are shown in green. There is also a process on each node called kubeprocessy that's not shown that sets up networking rules, connection forwarding for services, and pods and such on the host. Although networking and data storage services are shown outside of our nodes here, most functionality resides on the nodes themselves. You can also access the API server using a web interface called the dashboard via kubectl proxy. So this concludes the workloads on GKE section. And remember, in this section, we learned about pods and pod lifecycles. Welcome to the Securing Workloads on GKE section. In this section, we'll learn how Google Kubernetes Engine provides different ways to help secure workloads. Protecting them in Google Kubernetes Engine involves many different layers of the stack, including contents of your container image, container runtime, cluster network, and access to the cluster API server. So you'll learn how Google Kubernetes Engine provides these ways to help secure your workloads. In this section, we're going to learn about how Kubernetes allows users to quickly provision, scale, and update their container-based workloads. And in this section, we describe tactics that administrators and users can employ to limit the effect a running container can have on other containers in the same cluster, the nodes where containers can run, and the Google Cloud services enabled in user projects. Now, limiting the privileges of containerized processes is important for the overall security of your cluster. Google Kubernetes Engine allows you to set security-related options via the security context on both your pods and your containers. And these settings allow you to change security settings of processes like user and groups, available Linux capabilities, and the ability to escalate privileges. So let's talk about the 3 levels of configuration. Designing for security on Kubernetes Engine progresses in stages. It starts with broad concepts and concerns and ends with application-specific concerns. And project creation is less about Kubernetes Engine itself, more about creating the project, but it does have implications on your cluster design. Cluster creation is specific to Kubernetes Engine, and it remains agnostic to the specific application needs. Application deployment covers how to build and deploy images securely. And there are 3 tiers to secure your clusters and your projects. First and foremost, there are project level considerations. For example, how will they map to environments? How many projects will be used? Google Network Security features such as what types of access are required for each. And Kubernetes Engine security features. Not all are specific to Kubernetes, but these do have implications for cluster design. Speaking of clusters, there's cluster level considerations. These focus specifically on Kubernetes Engine. Securing access to the master node, for example, using private clusters, and securing worker nodes. Setting up the initial network policies to prepare for application deployment. These are all cluster level considerations. And speaking of application deployment, this covers how to build containers with good security practices, ensuring your Docker files don't go unintentionally run as privileged users on the system, and restricting container privileges at the OS level via capabilities and things like that. Secrets management and how to improve the privacy and security of sensitive data in the cluster. So all of these things are application deployment considerations for security. Now, Kubernetes Engine leverages a number of standard Google Cloud features and services, like projects, IAM, virtual private networks, all of which play a significant role in the security of a Kubernetes cluster. Kubernetes Engine's security begins with proper project design. How you design your GCP projects will have implications on later things and practices around things like IAM role design and network layout. Designing the infrastructure with security in mind provides the foundation for securing your clusters. Therefore, it's critical that an approach to security is taken that accounts for all levels of the infrastructure itself. Now, all GKE components are encrypted at rest. So this includes etcd, where secrets are stored. It also includes TLS for master to master and node to master communication. Integration with Calico provides network policy to control pod-to-pod communications, and private clusters make your master inaccessible from the public internet. Metadata concealment isolates workloads from node metadata. So let's talk about some key decisions you have to make when designing your cluster and cluster security. For example, do you have a clear understanding of the communication needs for your pods? If you do, then of course use firewall rules to allow only those connections, the ones you're expecting. Otherwise, the best practice is to block everything and then set up whitelists as connectivity requirements are discovered. Next item is, do your networking, security, and operation teams have conventions that need to be applied to your cloud networks? Maintaining these conventions not only reduces friction between the teams when moving into the cloud, but also reduces the changes that are going to be required to existing security processes and tooling, and make sure everything's compatible. Next, do you know from which networks your operators are going to require access to the Kubernetes control plane? Now, best practice says configure only the smallest set of authorized networks that will allow the operators to work and do their jobs efficiently. The next item is, has IP masquerading been enabled for all existing clusters? If not, you might ask yourself, well, why not? And can IP masquerading be enabled on all new clusters going forward? Is there a specific reason why they shouldn't? IP masquerading is highly configurable and generally doesn't have a downside. Existing processes should enable masquerading by default via enabling things like network policies. Now, the idea is to limit the default level of access that each workload or process on the node has within a cluster. For this, we can use service accounts specific to applications when they need to access things like the Kubernetes API. And these should provide the minimum number of privileges required as best practice. So it's best to use custom limited service accounts on nodes. Applications themselves should not use the node service account for resource access. And also for users, defining the minimal permissions required for their RBAC role is essential, following the practice of least privilege assignment. Now, Kubernetes itself supports two different kinds of authentication. User accounts are accounts that are known to Kubernetes, but are not managed by Kubernetes. For example, you can't create or delete them using kube control. Service accounts are accounts that are created and managed by Kubernetes, but can only be used by Kubernetes created entities, such as your pods. Now, in a Kubernetes cluster, Kubernetes user accounts are managed by Google Cloud, and maybe one of the following different types. You could have a Google account, or you could have a Google Cloud Service account. With either account, once authenticated, you need to authorize these accounts to create, read, update, or delete your Kubernetes resources. In order to follow the security principle of least privilege, you should always consider using Google Cloud Service accounts only if their capabilities specifically are required. Now, here we have an example that shows applying the principle of least privilege to a dev project set up for developers to build and test their upcoming features. It uses default roles provided by Kubernetes Engine. Here we have developers given read-write access to containers in the dev project by assigning them to the container.developer role and giving them those permissions. In the prod project, developers are granted only the container.viewer role. That gives them read-only access to the cluster because it's assumed that the operations staff will be the only ones that need to get in there and work with the cluster directly and have administrative privileges. Now, another way to help security and secure your Kubernetes master is to ensure that you are doing what is called credential rotation, and on a regular basis. When credential rotation is initiated, the SSL certificates and the cluster certificate authority are rotated as well. This process is automated by Google Kubernetes Engine and also ensures that your master IP address rotates. Now, credential rotation is considered a best practice for any secure system, since it limits the window of exploitation if your credentials are leaked somehow by mistake. Now, by default, Google networks are provisioned with reasonable security for the general use case. But understanding your specific needs allows you to add additional features and settings to increase the security of your networks. However, there are some key considerations, such as, do you have an IP addressing scheme used by established security tooling or processes? And if so, your network should be compatible with these tools, of course, to maintain current security levels. Next item would be what networks or IP addresses need to access the Kubernetes cluster nodes. You need to understand the connectivity requirements for your nodes. And also, who or what will need access to the Kubernetes control plane. Remember, access to the control plane is only required by users or tooling responsible for managing work nodes and, of course, the infrastructure. The next consideration might be, will any workloads need to be accessed directly by a pod IP rather than through something like a load balancer? Google Networking provides additional security features for when your workloads would be exposed by load balancers and therefore possibly vulnerable. So let's examine Google Network security features that can be implemented to meet your specific requirements. Custom networks. You can create and configure your own network to map to your existing IP address management convention. Following existing conventions, as we mentioned, will allow your network and security teams to more easily work with your cloud infrastructure. And firewalling. You can, of course, use firewall rules to control ingress and egress to your cluster network, as well as control communication between your subnets and node pools. Authorized networks. They restrict who can access your clusters and Kubernetes master endpoint. Authorized networks features block all connections to the master from public networks that have not been explicitly authorized. Aliasing and masquerading. IP masquerading prevents individual pod IP addressing from being exposed externally. IP addressing and aliasing allows the network layer to perform anti-spoofing checks on traffic. And these features further limit the accessibility of your workloads from the internet and also allow Google to perform additional security checks on the traffic itself. Now, a default network is created in your project. but it is recommended that you create and configure your own network to map to your existing IP address management convention. Now, aside from IP decisions, there are a couple other constraints to keep in mind when designing your network. For example, remember, subnets can span multiple zones, but they can't span regions. And to control communication between subnets, you'll need to create firewall rules allowing the traffic to pass between them. You can use the tags flag during cluster or node pool creation to appropriately tag your Kubernetes engine nodes for the firewall rules that you want to have taking effect. And in addition to firewalling, tags can be used to create routes between your custom networks. Now in auto mode, subnetwork routing between subnets is enabled by default. And with custom subnets, you'll need to create those rules and routes manually. So the next question might be, are the Kubernetes engine defaults right for you? Now, later versions of Kubernetes default to secure settings for most options. All of these settings should be reviewed when creating a new cluster to make sure they match your specific use case. For example, the control plane API provides administrative access to a cluster, and as such, access should be limited as much as possible to being from trusted networks only, as we mentioned previously. Public versus private IP addresses for nodes. Now, in many cases, the convenience of a public IP is really not worth the increased risk of attack. Node service accounts. Default service accounts may have a far broader set of permissions than you really require. And of course, we want to follow the principle of least privileges as a best practice. Consider accessibility of node metadata. Remember, metadata contains node credentials that could be exploited if your pod is compromised. So these are all considerations that you must take into account. Now, as far as restricting access to the control plane API, basic authentication should be disabled. It's far less secure than client certificates and IAM-based authentication. And the Kubernetes web user interface, aka the dashboard, is backed by highly privileged Kubernetes service accounts. Now, this is disabled by default in later versions of Kubernetes, like 1.10.0 and later. But the Cloud Console provides much of the same functionality, so you wouldn't necessarily need those additional permissions. Authorized networks limit non-GCP access to a specific set of being authorized addresses. And of course, restricting access to the control plane API is best achieved for the use of a private cluster and using these authorized networks. Now, we know that it's important to mitigate workload security threats, and we can do so by following these simple steps. First and foremost, remember, we want to restrict access to the control plane. This limits the damage that a malicious actor could do if they compromise a workload. Secondly, we want to limit access with IAM service accounts and private clusters. We want to follow the principle of least privilege, always, to ensure that each user and service gets access only to the resources they really need to do their job. This limits the damage and the risk if credentials from someone are leaked or exposed, or if a malicious user gets access to private clusters. We can use implicit firewall rules to block public access to your control plane and nodes. And of course, we want to provide defense in depth. So even if a vulnerability is discovered in the control plane, it can't be exploited from untrusted networks. So again, implementing private clusters. The third step, of course, is metadata concealment. It prevents compromised workloads from accessing sensitive cluster information. And of course, remember credential rotation. This again is going to reduce the amount of time that leaked credentials could be used to access your system. Now, we know that it's important to secure your workloads, and Kubernetes allows users to quickly provision, scale, update container-based workloads, but it's also important to limit the effect of a running container and what effect that can have on other containers in the cluster, as well as cloud services enabled in different user projects. Securing your workloads may involve limiting pod container process privileges, which is important for overall security of your cluster. And GKE allows you to set security-related options in the security context on your pods, as we mentioned, as well as on your containers. Now, binary authorization is a service that you can implement on GCP that provides software supply chain security so that you can automatically as well as digitally check each component of your software supply chain and ensure that the quality and integrity of your software is as it should be before it's deployed to your production environment. Another security feature is audit logging. Audit logging provides a way for administrators to query, process, and retain alerts on events that occurs in your Google Kubernetes Engine environment. Administrators can use the log information to do forensic analysis, real-time alerting, or possibly just for cataloging how a fleet of Kubernetes Engine clusters are being used and by whom. Now, by default, Google Kubernetes Engine logs all administrative activities. And you can optionally also log data access events depending on the type of operations you want to investigate. So, speaking of security, let's talk about some key decisions in assigning things like permissions and roles. First and foremost, what roles are required in each environment? Remember, generally you'll need fewer roles in development. Why? Because permissions could be defined more coarsely and role responsibilities could overlap because of the job that developers do. How do permissions for each role vary by environment, you might ask? Well, in development, you can use broader roles and permissions, but in production, you should always use fine-grained permissions and one role per set of responsibilities. Therefore, you're assigning only the privileges needed for that responsibility. You might also look at service accounts and what service accounts are needed for accessing Google Cloud Platform resources. Remember, service accounts should be defined for accessing applications that will be accessing GCP services like cloud storage and cloud pub sub and things like that. The other thing to consider is what permissions do your node roles require? Generally, nodes should only require minimal access to the GCP API. The next thing you need to, of course, remember is, have you applied the principle of least privilege when designing your roles? All roles at the IAM and RBAC level should be designed to follow this principle of least privilege. And the other thing to consider again is, have you enabled metadata concealment on your nodes? Metadata concealment should almost always be enabled. The next thing, of course, is, do you have a process for rotating cluster credentials in the event that they are exposed? Regular rotation, remember, is strongly recommended to limit the amount of time that someone could use those credentials to access your system. So this concludes our securing workloads on GKE section. And in this section, remember, you learned how Kubernetes allows users to quickly provision, scale, and update container-based workloads. You learned tactics that administrators and users can employ to limit the effect a running container can have on other containers in the cluster, the nodes, and of course, where the containers can run, and the Google Cloud services enabled in user projects.